Have you ever left a concert with your ears ringing? That ringing is your body's way of telling you that the sound was too intense. We experience sound every day, from whispers to traffic to concerts, but the range of those intensities is enormous. Today, I'll show you how we can use mathematics, specifically logarithmic functions, to make sense of that range. My name is Honor Culberson. I'm a junior at the University of West Georgia, and this is my presentation for Professor Patel's college algebra class. Thank you for joining me. Today I'll be presenting on one of our course objectives. But before we dive in, I want you to think about what sounds you heard today. Think about the quietest sound, maybe the ticking of a clock or the faint hum of a refrigerator. Now contrast that with the loudest sound you've heard, maybe a car horn or a door slam or even thunder. That enormous difference is exactly what we'll explore today, and we'll be using math, specifically logarithms, to do so. The course objective I selected is Model Real-World Situations. For this presentation, I'll focus on how logarithmic functions are used to measure sound intensity. This matters because sound intensity varies across an enormous range, from whispers to jet engines, and logarithms allow us to compress those values into something manageable. By modeling sound mathematically, we can better understand everyday experiences and even address important issues like hearing safety and audio engineering. Sound intensity is a perfect example of a real-world situation because it's something we all experience, yet it's invisible. You can't see sound waves, but you can feel their impact. By modeling them mathematically, we turn something abstract into something measurable and useful. And through that, we can make the invisible visible. Imagine starting your morning with birds chirping softly outside your window, then later walking into a crowded cafeteria where voices overlap and laughter fills the air. By evening, maybe you're at a concert where the speakers shake the floor. When you go to bed, you might have noticed the quiet rustle of pages turning in a home, the hum of electricity, the wind blowing outside, people laughing. Those louder sounds, like a jet engine or those speakers from earlier, can produce sound so powerful it causes pain or permanent damage to your hearing. The range can be hard to put into conceivable numbers without logarithms because those volumes are just so drastically different. That's in a single day that you experience all of those sounds, yet the intensity of those sounds span billions of times in difference. So without logarithms, those numbers are basically impossible to compare. If we tried to measure sound using raw intensity values, the numbers would be overwhelming. A whisper might have the intensity of 10 to the negative watts per square meter, while normal conversation is already a million times greater. At the extreme, a jet engine can reach about 1 watt per square meter. That's trillions of times stronger than a whisper. Comparing these values directly is nearly impossible, which is why we need a mathematical tool to make sense of them. To put this into perspective, if you stacked pennies to represent sound intensity, a whisper would be 1 penny. A conversation would be a million pennies, enough to fill a small room. A jet engine would be a trillion pennies, enough to cover entire cities. That's how overwhelming the raw numbers are, and why we need a smarter way to measure them. Now, let's introduce the mathematical tool that makes sound intensity easier to understand, the logarithmic function. A logarithm answers the question, to what power must we raise this base to get this number? For example, the logarithm base of 10 of 1,000 equals 3, because 10 raised to the third power is 1,000. What makes logarithms so powerful is that they compress these enormous ranges of values into smaller, more manageable numbers. On a graph, you can see that a logarithmic function rises quickly at first and then levels off, which is exactly what we need when dealing with sound intensities that span billions of times the difference. Think of logarithms like a zoom lens. If you're looking at something far away, you zoom in to make it manageable. Logarithms do the same thing with numbers. They zoom in on huge ranges and make them fit into a scale we can actually use. That's why they're perfect for sound. And we can solve another one step by step. We know that the power of 10 equals 2,500. Or we want to know what power of 10 equals. So to do that, we take the logarithm base 10 of both sides, and that gives us log of 2,500. So the log tells us the exponent. When we calculate, the answer comes out to about 3.4. That means 10 raised to the power of 3.4 is about 2,500. Hopefully that makes sense to you. Here is the formula that defines the decibel scale. The sound level, which we call L, is equal to 10 times the logarithm base 10 of the ratio between the sound's intensity and the reference intensity. That reference intensity is set at 10 to the negative 12th watts per square meter, basically the faintest sound a healthy human ear can detect. So what this formula does is compare any sound to that threshold, then compress the results into a decibel number that's easier to understand. Notice that the formula gives us a number, and that number gives us context. So every decibel value is relative to the quietest sound we can hear. So that means when we say 60 decibels, we're really saying this sound is a million times stronger than the faintest sound detectable by the human ear. So we went over the decibel formula. L stands for loudness in decibels, and then I is the sound's intensity. I0 is the reference intensity, which is, again, the faintest sound a healthy human ear can hear, written as 10 to the negative 12 watts per square meter. The formula says take the intensity of the sound, divide it by the reference intensity, then take the log base 10 of that ratio, finally multiply by 10, and that gives us the decibel value. So we're going to go over some examples. We'll go back and forth, but let's start with the whisper. The intensity of a whisper is about 10 to the negative 12 watts per square meter. Again, the threshold for human hearing. So if we plug that into the formula that we went over before, we get 0 decibels. But in practice, most whispers are a little stronger, so they measure closer to about 30 decibels. It's still very quiet, but notice how the decibel scale gives us a simple number we can compare instead of dealing with trillionths of a watt. So when we say that a whisper is about 30 decibels, think of it as the sound of leaves rustling or someone breathing quietly nearby. You'd miss it in a noisy room. Now we can look at a normal conversation. The intensity of a speaking voice is about 10 to the negative 6th watts per square meter. That's 1/millionth of a watt. When we compare that to the threshold of hearing using the formula, we get 60 decibels. That's why everyday conversation falls right around 60 on the decibel scale. It's loud enough to be clear, but still safe and comfortable. And then we can look at the jet engine example. The intensity there is 1 watt per square meter. When we compare that to the threshold of hearing, the formula gives us 120 decibels. Again, that is so loud that it can cause pain and even permanent hearing damage if you're exposed for too long. So that shows how the decibel scale takes a massive intensity value and turns it into a number we can easily compare. We can feel 120 decibels in your chest as a vibration. That's no longer hearing anymore, it's a physical reaction. That's why prolonged exposure at that level can cause permanent damage. Imagine that vibration you feel in your chest, in your ears. Pretty scary. Here's a chart that compares everyday sounds. A whisper is about 30 decibels, a normal conversation at about 60, traffic noise closer to 80, a concert can reach about 110, and a jet engine tops out at about 120. Notice how these decibel values are easy to compare, even though the actual intensities that we went over earlier differ by billions. And that's the beauty of a logarithmic scale. It takes enormous range of raw numbers, then compresses them into something we can understand at a glance. Without them, we'd be stuck comparing trillionths of a watt to whole watts. With them, we can say, okay, a whisper 30, conversation 60, concert 110. Simple, manageable, easy to understand. One important point to understand is that our ears don't respond to sound in that straight linear way. Doubling the intensity of a sound doesn't make it feel twice as loud. Instead, our perception of loudness is logarithmic, meaning we naturally experience sound in those compressed steps. which is why the decibel scale works so well. It's not just math for the sake of doing math. It actually mirrors how our hearing interprets changes in intensity. For example, if you turn your music up from 60 decibels to 70, it doesn't sound twice as loud, it just sounds louder because our ears are wired to respond logarithmically. Now, let's talk about hearing safety. Research and workplace safety guidelines show that sounds above 85 decibels can start to damage your hearing if you're exposed for long periods. That means everyday situations like heavy traffic, loud concerts, or even listening to music through headphones at a high volume can put your ears at risk. This is why understanding decibels is important. It helps us recognize when sound levels are safe and when we need protection, like earplugs or volume limits. Think about how often we ignore this. I know I do. I can wear headphones for hours at volumes that exceed 90 decibels. That's louder than city traffic. Over time, this can cause permanent hearing loss. But by knowing the math, we can make smarter choices like lowering the volume or taking some breaks here and there. In recent years, technology has made use of the decibel scale all the time. Sound level meters, for example, measure noise in workplaces or cities to make sure that it's safe. Your phone, especially if you have an iPhone, it can track the volume of your environment or even your headphones, warning you if it's too loud. And in audio engineering, software uses decibels to balance music tracks or adjust microphones. All of these tools rely on logarithmic functions to translate that raw sound intensity into numbers we can understand and use. A fun fact is when DJs or sound engineers mix music at a concert, it can kind of look like they're just tuning knobs and flipping switches and you have no clue what they're doing. But part of it is watching decibel levels to make sure that the bass or anything else doesn't drown out the vocals, which is super interesting. And city planners use decibel readings to decide where to place sound barriers along the highway. Even your phone, going back to your phone, it has built-in tools that measure sound because protecting your hearing has become a public health priority to ensure that less and less people suffer from massive hearing loss. It's also worth looking at the history. The decibel scale was developed in the early 20th century by engineers at Bell Telephone Labs. They needed a way to measure signal loss in telephone lines, and raw intensity values were too unwieldy. By using logarithms, they created a scale that was practical and intuitive. That's why they call it decibel, named after Alexander Graham Bell. To summarize what we've covered, logarithmic functions are powerful because they take enormous ranges of value and compress them into something manageable. The decibel scale applies this idea to sound, turning raw intensity into numbers we can easily compare. This has real-world importance in protecting our hearing, in audio engineering, and in simply understanding the sounds we encounter every single day. So, to make sure that we understand the logarithmic function, we should go back to our example of a conversation. Let's look at that. A normal conversation. The intensity is about 10 to negative 6th watts per square meter. So we divide that by the reference intensity, 10 to the negative 12th, and that gives us 10 to the 6th power. The log of 10 is to the 6th is 6. Multiply by 10 and we get 60 decibels. So a conversation is 60 decibels. And we can apply this to anything. So we can go back to our example of a jet engine. The intensity is about 1 watt per square meter. Divide that by the reference intensity, so 10 to the negative 12th. That gives us 10 to the 12th power. The log of 10 to the 12th is 12. Multiply by 10, and we get 120 decibels of pure hearing damage. So yeah, hopefully this makes it where you understand the concept a little bit better and are able to do the math on your own. In conclusion, logarithmic functions gives us a way to handle extreme ranges of value, and the decibel scale shows us how this applies directly to sound. By compressing raw intensity into simple numbers, we can understand, compare, and manage the sounds around us. This has practical importance for safety, for technology, and for everyday awareness. So the next time you're at a concert, you're adjusting your headphones, or even noticing the quiet whisper, remember that there's math behind that experience. Logarithms are helping you hear the world differently. And that's the beauty of this course objective. Modeling real world situations is about seeing the math that is woven into everyday life and getting it out of the classroom. So I want to thank you for listening. I hope that you learned a lot and you had a great time. I'll be uploading this to YouTube. And yeah, I'm very excited about it. I have Tourette's and a stutter, so I'm very shocked that I got through this, but I hope you enjoyed listening as much as I enjoyed creating it. So, yeah.